Hey guys, welcome back to my YouTube channel. I am Karthik Agrawal, currently studying in Sri Venkateswara College of Engineering. I hope you all are in great health. Today, we are diving into the fascinating world of Boolean logic and how it powers the digital world around us. We will break down the key concepts and principles covered in the research paper, what is Boolean logic and how it works by Barman Zuri and Mohammed J. Magdum. Let's explore how Boolean logic forms the foundation of computing. First, let's see the contents of the research paper. We would be giving a short introduction, then explain bits and bytes, base 2 and 8-bit system, standard ASCII set, byte prefixes and binary math, logical gates, simple adders, full adders, truth table, practical implementation, and finally we are going to give a small conclusion. First, let's talk about the origin of Boolean logic. It was developed by George Boole in mid 1800. Boolean logic is the foundation of modern computer operations, transforming logical statements into bits, binary values of zeros and ones. It all started with Boole's simple yet revolutionary idea, which later formed the basis of digital circuit design. Now, let's discuss how bits and bytes work. A bit is the smallest unit of data in computing. It is either a 0 or a 1. 8 bits form a byte, which can represent anything from a letter to a number. Essentially, computers use the base 2 binary system to store and process these values. In the system, data is handled as sequential of zeros and ones. Now, let's understand what is base 2 and 8-bit system. In base 2 system, only two digits that is 0 and 1 are used. This makes sense for computer because they deal with electronic circuits that are either at on or at off, that is 1 or at 0. When 8 binary digits are grouped together, they form an 8-bit byte, allowing computers to store 256 different values. This system is essential for processing, storing, and transforming informations in computing. Now, let's understand standard ASCII set. The ASCII character set is standard used to assign numbers to text characters. ASCII stands for American Standard Code for Information Interchange. Now let's consider an example. The letter A is represented by the binary number that is 01000001 or 65 in decimal. ASCII uses 7 or 8 bits to represent character, allowing computer to store and handle text in files, memories, or when transmitting data. Now, let's move on to byte prefix and binary math. You have probably heard terms like kilobyte, megabyte, or gigabyte when describing the file size or storage. As you all can see, 1 kilobyte is equal to 2 to power 10, that is equal to 1024 bytes. Similarly, 1 megabyte is equal to 2 to the power of 20 and 1 gigabyte is equal to 2 to power 30. This binary math helps us to describe large amounts of data in computing. The reason computers use base 2 math is due to simplicity of representing binary values in electronic circuit. Binary math operates similarly to decimal math except each bit can hold a value of 0 or 1. For example, binary addition follows the same logic as decimal addition, with carries happening while adding bits results in 2. Now, let's understand logic gates. Logic gates are the fundamental building blocks of Boolean logic. This paper explains basic gates such as AND, OR, and NOT, along with some complex gates such as NAND, NOR, XOR, and XOR. And these gates allow us to manipulate binary values and perform tasks like addition, comparison, or decision making in computers. For instance, an AND gate output is always is true only if both inputs are true. Now, you all can see in the following image different the symbols for the logic gates along with their mathematical expressions. Next, let's look at simple adders, which is also known as half adder. These circuits perform binary additions for two single bytes. When adding binary values like 0 and 1, you get 1. However, when adding 1 plus 1, you would get 1 0, binary of 2, which produces a carry value. Simple adders provide a sum and carry, but they don't handle more complex multi bit operations. As you all can see, the truth table for the simple adder and the semantic representation of the simple adders. Now, for full adders, a full adder can add three inputs, two binary digits, and a carry input from a previous addition. This makes full adder essential for adding larger numbers. By connecting full adders together, we can perform multi bit binary addition, which are fundamental for arithmetic operations in modern computing. As you all can see from the following image, the circuit representation of full adder. Now, you all can see the logic table for full adder. The logic table for full adder considers all possible combinations of A, B, and carry input, producing the appropriate sum and carry output values. As you all can see, when A and B is equal to 1 and C is equal to C and Ci is equal to 0, that time the Q, which is nothing but sum, is equal to 0 and Co is equal to 1. Q can be 1 when all three A, B, and Ci are 1. I hope you all have understood till now simple adders and full adders. Now, let's move on to the next topic, that is truth table. A truth table is a way to represent all possible outcomes of Boolean expression or Bool logic gate. For example, in an AND gate, the truth table shows that the output is true only when both input are true. Truth tables are incredibly useful for understanding and visualizing how Boolean logics behave under different conditions, simplifying the design of complex circuits. As you all can see, I have two inputs such as A and B, and you can see the respective truth tables for under the logic gates of AND, OR, NOT, NAND, NOR, SOR, and XNOR. These tables are fundamental tools in logic circuit design, helping engineers to predict how their circuits will behave. Finally, let's look at some practical applications of Boolean logic. From building security systems to running search engine queries, Boolean logic powers system we use daily. In a security system, for example, Boolean expressions can ensure the alarm only triggers if certain conditions are met, like the door is open and it's nighttime. Similarly, search engines use Boolean operators like AND, NOR, and NOT to filter the results. If you search for apple and orange, the search engine will return only the results containing both of words. In computing, Boolean logic underpins everything from simple decision like turning on a light when a sensor detects motion to complex tasks like data encryption and artificial intelligence. Now, as you all can see, the following example, that is considering a security system that operates on two variables p, that ensures whether it is a daytime or not. If it is a daytime, it shows true, that is 1, and If it is night, it shows 0, that is false. Similarly, the variable q, which stands for whether the window is open or not, and if the window is open, it displays true, that is 1, and false means 0. Now, using the Boolean logic, the system might activate if it's nighttime and the window is open. As you all can see the following truth table and circuit representation of the system. Now, I would like to conclude saying Boolean logics may seem complex at first, but as we seen today, it is actually the simple backbone of almost everything we do with technology. If you want to dive deeper into this topic, check out the full chapter linked in the description. Don't forget to like and subscribe for more interesting videos.